Now let's take a look at a type of function called a piecewise defined function. So from the name you can tell that this is a function that is defined in pieces. Whenever you have a piecewise defined function, you have one function. In this case, we have the function f. This function is defined in several pieces. So each piece is given by a formula, and when you use that formula is given after the formula. So let's take a look at an example. Here we have the function h, and is defined in two pieces. The first piece is x squared minus 4, and we use that as long as x is less than or equal to 1. If x is bigger than 1, then we use the absolute value of the quantity x minus 3 to find our y value. So let's take a look at part A. We are to find h of 3. So notice 3 is our x value. Now, that should tell us what piece to use, because we use the first piece if x is less than or equal to 1. We use the second piece if x is bigger than 1. Well, here x is 3. So you'll notice that 3 is bigger than 1. So we should use the second piece. So we will go ahead and use the absolute value of x minus 3. But what is x? X is 3. And the output then is going to be the absolute value of 3 minus 3, which is the absolute value of 0, which is 0. In our second part, in part B, we have x equals 0. This time, we know that since x is 0, that's less than or equal to 1, so we should use x squared minus 4. So we have 0 squared minus 4 to obtain negative 4 for our y value. Now lastly, we have x is 1. Now if x is 1, which piece do we use? We use the first piece because 1 is less than or equal to 1. It satisfies this first condition. So we should go ahead and use x squared minus 4. So we get 1 squared minus 4, which is going to be negative 3. So here we are given a function f, and it is defined in two pieces. We are to find the domain of the function. So the best way to think about this is to split it up into each piece. So let's look at them separately. We have y equals negative 3/4 x minus 2. And then we have the equation y equals x squared. If we think about these outside the context of the piecewise defined function, then this is a line, and its domain is all real numbers. So nothing has to be excluded there. Y equals x squared. This is our parent function, y equals x squared. And this is, again, a domain of all real numbers. So no difficulties exist there in either one of them separately. But now let's consider them together. If we consider them together, then there are no problem spots, and so therefore the domain will be all real numbers. Or if we think about it in terms of interval notation, we have negative infinity to positive infinity. So how do we find any intercepts? So let's look at them separately again. Y equals negative 3/4 x minus 2. And we'll find the intercepts of that. So for the x-intercept, we let y equal 0. If y equals 0, we have 0 equals negative 3/4 x minus 2. We can add 2 to both sides. multiply both sides by 4, and then divide by 3. So the question is now, notice this is an x value. That is negative 2 2/3, and negative 2 2/3 lies in this condition. So therefore, since this satisfies this, it does relate to the piece that we just used. So we do have an x-intercept there. Now what about any y-intercepts? A y-intercept would be if we let x equal 0. So y would equal negative 3/4 times 0 minus 2. But that would mean y would equal negative 2. Now, notice again, x equals 0. We can go back to that condition. Is 0 less than or equal to negative 1? No. So therefore, this is not the y-intercept associated with our function. Okay? So now, let's look at the other piece. Y equals x squared. So y equals x squared, let's find the x-intercept. We can let y be 0. So if y is 0, that means that we would have x squared equals 0. That would mean that x equals 0. If x equals 0, which piece do we use? We use the bottom piece. So notice that x equals 0 corresponds to this second piece, which is the one that we just used. So that one is okay. Now let's look for the y-intercept. So the y-intercept is if we let x equal 0. So if x equals 0, we would have y equals 0 squared, which is 0. Now again, check x equals 0. Where does that sit? That's on the second piece, and that's the formula that we used. So we do indeed have a y-intercept of 0. So let's summarize all of this. We have an x-intercept of x equals negative 8/3, and that's from the first piece. We also have from the second piece an x-intercept of 0, and then we have a y-intercept of 0. So this negative 8/3 comes from our first piece. Negative 2 as a y-intercept doesn't cut it because it comes from the first piece, but x doesn't equal 0 there. And then our second piece gave us an x-intercept of 0, and our y-intercept of 0 comes from the second piece as well. So now let's graph this function. So we already know a couple key pieces of this. We know that we have an x-intercept of negative 8/3, which is negative 2 2/3. So that is roughly there. We also have x equals 0 and y equals 0. So those yield the same point at the origin. So how do we graph a piecewise defined function? Well, we separate them. We separate the two pieces. We look at y equals negative 3/4 x minus 2. And then we will look at y equals x squared. Now, if you are taking notes in pen, I highly suggest that you wait or that you go grab a pencil, because we will graph and then we will erase. That's the best way to graph a piecewise defined function. We have already said that y equals negative 3/4 x minus 2 is a line. This line has a slope of negative 3/4, and it has a y-intercept of negative 2. So if we go ahead and look at those features on this graph, on this coordinate plane, so we have y equals negative 2, and then we have a slope of negative 3/4. So that means that we can go from this point down 3 and to the right 4. So down 3 to the right 4 yields for us this point. We could also go up 3 and to the left 4. So if we go up 3 and to the left 4, we land here. Now let's connect those points. And you'll notice that it will go through that x-intercept of negative 8/3. So now this is the thing that we have not yet taken into account. This is only for x is less than or equal to negative 1. So this means that whenever we come over here, we look at where x equals negative 1, which is right here, all along this vertical line. And we only want our piece of this line to be at negative 1 or to the left. So we will erase anything. Here, it might be beneficial. Let me go ahead and make that division on the graph, on the coordinate plane. This is x equals negative 1. This is the boundary between the two pieces. So this piece, y equals negative 3/4 x minus 2, is only good as long as x is less than or equal to negative 1. So as long as the piece is at this line or to the left. So we need to erase everything to the right. Now, notice that this piece is okay at x equals negative 1. So we will end this line with a closed dot. And we'll signify that this goes forever to the left with an arrowhead. Now, y equals x squared is our parent function, right? And it's not been shifted anywhere. So let's go ahead and graph it. We have the guide points, negative 1, 0, 1, yield 1, 0, 1. So let's go ahead and plot those. But, again, we have to consider the fact that this is only good as long as x is greater than negative 1. So we have that demarcation on our coordinate plane of x equals negative 1. We only want this piece of this squaring function to be to the right of negative 1. So let's erase anything that's to the left. And what about at negative 1? At negative 1, this piece does not work. It's only on the first piece where x equals negative 1. So we will go ahead and erase that point, and we will instead mark out an open circle, a hole on the graph. And then we can go back and we can erase that x equals negative 1 line. So now we have our function. Now, a quick question based upon what we have here. I want you to think to yourself and answer this question. How many functions have we graphed? I'll pause while you think through it. Now the answer is found right here. We have graphed a single function, but it's a function that's been defined in two pieces. So we see two pieces, but it's one function. Now, we need to think about the range of this function. So go ahead and write the range of this function, which is in interval notation from bottom to top looking at the y values. So smash everything to the y-axis and see what you get for the range. So go ahead and pause and do that. You should obtain -1, which is included, all the way to infinity. You might think, well, what about 1? Shouldn't there be a break there because I have this point? And the answer is no, because that y equals 1 is filled in over here and even over here. So even though there's a break right here in this piece, we still cover it by other pieces of our function. Now let's look at another. So as we look for the domain of this function, we have three pieces. We have y equals 2x plus 3. We have y equals 1. And we have y equals x squared plus 1. So this is a line. This is a horizontal line. It's the constant function. And then we have a squaring function that's been shifted up 1 unit. Now, the domain of each of these is negative infinity to infinity when considered separately. So we have no problems. Now let's combine them together and look at the whole thing. So this piece is defined from -4 to -1. There are no problems on that interval itself, so we can include everything there. Y equals 1, there are no problems in this interval, and y equals x squared plus 1 is good for anything 1 or above. So we consider just all of these are okay, and so the domain will be anything that's in those three. So -4 to -1, but then -1 is picked up in our second piece and it goes to 1, and then 1 is picked up in our third piece and it goes, our third piece, all the way to infinity. So -4 all the way to infinity is the domain of the whole. What about intercepts? Well, let's look at our first piece, y equals 2x plus 3. So for our x-intercept of that piece, we'll let y equal 0. And so that gives us 2x plus 3 equals 0, which is x equals -3/2. Now, is -3/2 in this interval? Well, it's -1.5, which is indeed in that interval. So this is okay. Now, let's look at our second piece. We have y equals 1. Now, you might be asking, why is he not doing the y-intercept? Hold on, and I'll explain. So for y equals 1, let's go ahead and find the x-intercept. We can let y equal 0. That would mean that 1 equals 0. There is no x-intercept for y equals 1. This is not true. There is no solution to that. So there's no solution, so there is no x-intercept for that. Now let's look at our last piece, y equals x squared plus 1. Let's look for the x-intercept. That would be, again, if we let y equal 0, we would x squared plus 1 equals 0. X squared would equal -1 which has no real solution. That means that there are no x-intercepts there. So the only x-intercept that we have is x equals negative 3/2. Okay, now why did I not touch the y-intercept? Well, for any function, the y-intercept is when x equals 0. So let's let x equal 0. I don't have to worry about all three pieces because I only have to worry about the piece where x is allowed to be 0, namely on this middle interval. So we are looking at f of 0, which is 1. And that is our y-intercept. So let's go ahead and see all the information that we have at this point. So our x-intercept, we only have one. It is x equals negative 3/2. Our y-intercept is y equals 1. Now let's graph this function. First, I'll go ahead and plot the points that we already know from our x and y-intercept. So x equals negative 3/2, y equals 1. Now, we have the three pieces again. Y equals 2x plus 3, y equals 1, and y equals x squared plus 1. So here we have a line. Its slope is 2, and its y-intercept is 3. So let's go ahead and plot that out. We have y equals 3, and we have a slope of 2, which means that we can treat that as 2 over 1. So up 2 to the right 1, up 2 to the right 1, or we could go down 2 to the left 1, down 2 to the left 1, so on and so forth. So if we go ahead and connect those, that's what we obtain, but we need to erase. So notice that this piece is only valid for when x is between negative 4 and negative 1. So if I make those marks on my graph, in my coordinate plane, there's when x is negative 4, and when x equals negative 1, we're here. So we need to erase anything outside that. And we only will look at in between. Now, if x equals negative 4, then we're okay. We should put a closed dot there. If x equals negative 1, we should put an open dot on the right. So now, what about y equals 1? This is a horizontal line. And so therefore, it's going to go from 1 to 1. Actually, if we just think about it as a horizontal line first, that would be this whole horizontal line. But that's only good for when x is between negative 1 and 1. So let's go ahead and erase anything outside negative 1 to 1. And again, if it helps, we can go ahead and mark out where those x equals negative 1 and 1 boundaries are. So we should erase anything outside of that. Now, since x equals negative 1 is allowed on that second piece, we can put a closed dot on that left point of that piece. So it fills in the dot from the previous piece. And then on the right, we're going to have an open circle because x is not allowed to be 1 on that piece. Now let's look at y equals x squared plus 1. So let's go ahead and plot some points. We'll learn a quicker way to plot this or graph this in the next section. So if I just go ahead and put in some values, we have negative 1, 0, 1, and 2. That will yield for us negative 1 squared is 1 plus 1, 0 squared plus 1, 1 squared plus 1, 2 squared plus 1. And because this is based off of the parent function, we should get a very similar shape. So let's go ahead and see what we get. We get a U shape. -1 goes to 2. And then we have 0, 1, 1, 2, and then 2, 5. Now, we want this piece to only be for x is bigger than or equal to 1. So we erase everything outside of that. And what we can do is, x is allowed to be 1 on that piece, so we'll put a closed dot on that portion. So now I'm going to erase all the green boundaries. Too much. It was closed. And so here is our function. So it is a function in 3 pieces, and it's pretty interesting that the first piece had a hole, but the second piece filled it in. But you'll see that that domain that we had from -4 to infinity is indeed the domain that we see here. And we do see our x-intercept and our y-intercept. Now go ahead and pause the video and find the range of this. If we smash everything to the y-axis, what do we get? Well, this piece would go to -5, and we would continue on up until 1, which there is a break then. So -5 to 1, we include the -5, we're including the 1, but then there's a break between 1 and 2. And then we pick back up at 2, and we don't stop. We continue on. So we have 2 to infinity. And so we'll put the union symbol between those.